In the previous lecture, we saw the shortest path problem. We modeled the shortest path problem as an integer program and proved some things about it. Really, the shortest path problem is going to be an introduction to the real problem we'd like to study, which is the maximum flow problem. In the maximum flow problem, we're given a graph, g equal to VA, which is again a directed graph. We're also given capacities on each one of the arcs. The capacity is going to be an upper bound, U of A. We're given a start node S and a termination node T. Hopefully the parallels between the input of the shortest path problem and the max flow problem are apparent. The objective in the maximum flow problem is to find a flow from S to T so that a few things are satisfied. The first is flow balance. For every node not equal to S or T, the flow into it is equal to the flow out. For the node S and T, the flow out of S is equal to the flow into T. So there's a balance between the flow out of S and the flow into T. There's also a capacity constraint. For every arc, we can have a flow on that arc A of at most U of A. Finally, we're interested in the flow that satisfies all these constraints that has a maximum value, and we're going to denote the value of a flow as the value of the flow out of S. In the graph on the side here, we have a particular instance of the problem. We've drawn the graph with all the arcs, we've noted S and T, and the numbers next to each one of the arcs are the upper bounds. We can find a flow through this, and we'll do it incrementally. Although I already have the optimal flow in mind, I'll explain how the flow is going to work through the graph. Out of S on this first arc, we're going to push a flow value of 2. This flow is going to hit the next node, and from this next node, we have to have flow conservation, so the amount of flow in, 2, has to equal the amount of flow out. So I put a flow of 1 on each one of these arcs. We go to this one arc, and there's only one way for the flow to come out, so we put a flow value of 1. On the other node, we have a flow value of 1 coming in, and we potentially have a flow of 1 coming out in order to satisfy flow balance. We see that the flow balance between S and T is so far satisfied. But this isn't the maximum flow. We can actually put additional flow through this network. The way we're going to do it is we're going to push another 2 units of flow outside of S, and from this we're going to push 1 unit of flow onto each one of these corresponding arcs. We're going to push 1 unit of flow along this bottom arc, and we're going to update the flow along this middle arc from 1 to 2. This again is a flow, and we've satisfied all the flow balance constraints. And again, the flow out of S is the flow into T. In this case, the value of our flow is going to be equal to 4. And although we've arbitrarily said that the value of the maximum flow is the flow out of S, it could equally well have been the flow into T, since those two are the same. It turns out that the flow problem is a powerful modeling tool, and it's a modeling tool in the following way. For a lot of problems, we can cast it as a flow problem, and then use algorithms for maximum flow problems to solve the original problem. For example, in the shortest path problem, we can model this as a flow problem that we'll discuss later, and by solving that flow problem, we solve the shortest path problem. In general, this is a powerful modeling technique because the algorithms to solve flow problems are very fast. In addition to being a powerful modeling tool, we can also model the flow problem itself as a linear program. The algorithms for solving maximum flow problems are faster than the general algorithms for solving linear programs, so whenever we're casting a problem as a flow, we're generally going to use something other than a linear program to actually solve it. However, when we prove things about flows, we're going to rely extensively on the LP formulation. In the linear program formulation, we're going to have a variable for the flow along every arc. So the flow from node I to J is going to be Fij. Our objective is to maximize the amount of flow that comes out of our node S, which is the sum over all I of the flow from S to I. For every arc, or for every node rather, we have to satisfy the flow balance constraint. That is, the flow into J is equal to the flow out of J for every node that's not equal to S or T. S and T, we let them be free. In this case, we're maximizing the flow out of S, and naturally the flow into T is going to be the same as the flow out of S. That's because if we sum this flow balance constraint over the entire network, we can see that the flow out of S is equal to the flow into T. So we don't write that constraint explicitly. The final constraint tells us that the flow along any arc is at most the upper bound. These constraints together formulate the flow problem as a linear program. In addition to modeling this as a linear program, we could potentially model this as an integer program. In some cases, we would like the flow along every arc to be an integer. In this case, we have the same objective value, the same constraints, and all we do is say that the flow now has to be some integer value. By modeling this as an integer program instead of a linear program, we can potentially increase the amount of time it takes us to find the optimal flow. One nice property of flows, though, and the linear program in particular, is that if all of the upper bounds, uij, are integer valued, then the flow values are actually integers. This says more than just that the optimal solution is going to be an integer, that is, the objective value is going to be an integer. The flow along every arc is actually going to be an integer. This is a powerful property, and if we were to study flows in more detail, we would prove this. In this course, we're going to prove this as a result of a much more powerful theorem about linear programs. The maximum flow problem we discussed is actually a special case of a more general problem called the MinCost Flow problem. We discussed the max flow problem first because it's more understandable, but also because the algorithms to solve it are much faster and occasionally more understandable. MinCost flow problems add a little bit of additional computation. In the MinCost flow problem, we're still given a graph, G equal to VA. This is a directed graph, and we have capacities on all of the arcs. The difference now is that along each one of these arcs, we also have an additional cost. So there's an upper bound to the flow that goes across an arc, but also a cost for every unit of flow that we push across an arc. And also, instead of having a particular node, S and T, that we try to send flow between, we're going to have demand values, which can either be positive or negative, for every node in our network. Potentially, these could be 0. The objective of the MinCost flow problem is to find a flow such that the flow in minus the flow out is equal to the demand. That is, flow balance is preserved, except now we have a little bit of extra, the demand, that we need to keep in that particular node. We also have that for every arc, the flow along that arc is at most the upper bound of flow on that arc, UA. And finally, we'd like a minimum cost flow. Here, the cost of a flow is the amount of flow along every arc multiplied by the cost per unit flow of that arc, CA, summed over all the arcs. Here we have a particular instance of the MinCost flow problem. The graph is in black. Adjacent to every vertex is the demand on that vertex, and we note that the demands are both positive and negative. The cost of an arc is written in blue, and the capacity of an arc is written in green. We know ahead of time what the optimal flow is here, and I'm going to write it in and explain it as we go why the flow values are the way they are. One thing to note before we start writing the flow is that the sum of the demands at all the vertices is equal to 0. It's a simple exercise to prove that the only way to satisfy our flow balance constraints is to have the sum of the demands at all the vertices equal to 0. Otherwise, there is no feasible MinCost flow. Since we verified that there is a MinCost flow, we can start writing it. We'll start with the node that has -3 demand. Having -3 demand means that 3 units of flow have to be leaving this node. We'll send 2 of the units of flow along this one arc. This arc has an upper bound of 2 and a very low cost. We'd like to send as much flow as we can across it, but we can only send 2 or else we'll violate the upper bound. The rest of the flow is going to be sent along this bottom arc. This bottom arc has a very high capacity but a very high cost, so we don't want to send much flow across it. Now we can consider the top node that has an initial demand of -1. There's an initial demand of -1, but now 2 units of flow are coming in, so we can treat this as having -3 units of demand. Now 3 units of flow have to come out of this arc. Those 3 units of flow have nowhere to go, and we can only push them across this bottom arc. Once we do that, we've pushed 3 units of flow into this node that initially had a demand of 2. Because it initially had a demand of 2, and 3 units are coming in, we have 1 unit that we have to push out, or -1 unit that we have to push out. This 1 unit is only going to go down to this lower arc. It's going to go across this lower arc because there's enough capacity and the cost is very low. When we look at our bottom arc, or our bottom node rather, we see that it has a demand of 2 and a total flow into it of 2, and so the demand is satisfied at this node 2. If we look at all of the nodes together, we see that the total demand is satisfied at each one of the nodes. That is, the sum of the flow in, flow out, and the demand at that node is equal to 0. Now we can compute the objective of this flow. The cost of this flow is equal to the flow across each arc times the per unit cost of flow. This gives us 2 times 1 plus 3 times 3 plus 1 times 2 plus 6 times 1. And if you're quick enough doing the math, this is equal to 19. So our total cost of our flow is 19. It turns out that this is the MinCost flow inside of this network. We should note that as we were doing the flow, there was some explanation of why the flow was going along the particular arc it was. These are just intuitions and not an algorithm. We're not going to give an algorithm for the MinCost flow problem because we're just going to model it as a linear program and potentially solve that linear program. There's enough packages out there and enough knowledge about how to solve these problems that we're not going to go through it in this course. We're simply going to use it as a modeling tool. Not surprisingly, there's a linear programming formulation for the MinCost flow problem. It's very similar to the formulation for the max flow problem. The difference is in the objective function. Here we have a flow value, but now we multiply the flow value times the cost of pushing flow across an arc. The other difference is that in our flow balance constraint, we now write a flow balance constraint for every node. We don't exclude S and T. And the flow balance, instead of being equal to 0, is equal to the demand at that particular node. We retain the capacities on each one of the arcs. That is, we can't have more than Uij flow across arc ij. The MinCost flow problem retains the same integrality property that the max flow problem has. Namely, if the Uijs are all integers, that is, all the upper bounds are integers, and the demands at every node are integers, then we have an integral optimal solution. And this is again more than just the objective value of our linear program. This says that the flow values across each one of these arcs is integer. We won't write the integer programming formulation for this, but there is a corresponding integer program formulation. Usually, because of this integrality property, it's not necessary to solve any sort of integer program related to MinCost flows.